So what's a joint PMF? Can someone repeat the definition of a joint PMF for us? Yes, please, because you were here last lecture, I know. Yes, you or you. Go ahead. We have two different random variables. Okay, so for each pair of values, x, y, the probability that the first random variable takes the value x, while the second random variable takes the value y, is the joint PMF of x and y. So what's next? Let's do this example. Consider the joint PMF of x and y, which take positive integer values in this range. X plus y is between 1 and 3. 1 is not included, 3 is included. So what kind of region is that? It looks like a triangle, yes. So if x and y are the horizontal and vertical axes, then the values that are in consideration, first of all, let this be 3, and let this be 3. Okay, 3, 0 is included, yes? Positive integers, very nice. So 3, 0 is not included. Let's see. 2, 1, 1, 2, 0, 0. Okay. Is 2, 0 included? No. So this axis is not included. This axis is not included. Is 2, 1 included? Yes. There are positive integers less than or equal to 3. The summation is less than or equal to 3. 1, 2 is included. 1, 1 is included. Anything else? No. Okay, it's a simple distribution. Simple joint distribution. What, 2, 0? No, because they are positive integers. Okay. So only these three values. And the PMF is uniform on these values, meaning all these points are equally likely. What should the value of their probabilities be? 1/3, because there are 3 points. So C is 1/3. Right? Otherwise, the joint PMF, when you sum it, overall values would not add to 1. Okay, so C must be 1/3. Find the marginals. What's a marginal? We name the distribution of x and the distribution of y as their marginal distributions in order to distinguish them from the joint. Let's find Px of x. Px of x, well, how many values can x take? X is either 1 or 2. That's it. If you look at x, for all y, x is 0 is not possible. X is equal to 1 is possible, and x is equal to 2 is possible. Okay, x is equal to 1 includes 2 different events. X is 1 and y is 2, or x is 1 is y and y is 1. So the probability that x is equal to x is the sum of these 2 probability masses. If you want, you can think of this picture as 3-dimensional with the 3rd dimension coming out of the board. So you can think of probability masses like this coming out of the board that are all at equal height. Okay? So the sum of these 2 is 1/3 plus 1/3. 2/3 is the marginal PMF of x at 1. The marginal PMF of x at 2 is just this. Okay. So sum over all y, the probability, the joint PMF pxy, you get 1/3. Okay. Let's plot this. Let's plot this over here. Px of x as a function of x. X is either 1 or 2. The probability that it is 1 is 2/3. The probability that it is 2 is 1/3. Okay? Now, if you look at this picture and this joint PMF, what do you see? This picture is obtained by summing the weights along the y dimension. Okay. It's also like you look from this direction at the joint, the three-dimensional joint PMF, and for every value of x, you just combine all the weights along the y direction, and you get this picture. Let's do the same for y. Py of y, the marginal PMF of y. What is Py of 3? 0. Py of 1? Py of 1. Can y be 1? Yes, y is 1 if x is 1 or 2. So Py of y is 1/3 plus 1/3, which is 2/3, when y is 1, and is 1/3 if y is 2. It's 0 otherwise. Okay. In this case, the situation is symmetric, and the marginal PMFs of x and y come out to be the same. Doesn't have to be this way. Okay, it's a special case in this example. Okay, are there any questions? Okay. Last lecture we said a function of a random variable is also a random variable. Now we have two random variables. Natural extension is to consider a function of two random variables. A function of two random variables, or any number of random variables for that matter, defined on the same sound probability space, is a random variable itself. So in this example, z is a function g of x and y, where x and y are random variables with a well-defined joint PMF. If you want to find the PMF of z, all you have to do is sum the probabilities of all xy pairs that result in a value little z for this function. Okay? So, in other words, the marginal of z, pz of z, is the sum of the joint PMF pxy xy over all xy pairs such that the function g evaluated at this xy pair is equal to z. Okay? If there's only one such xy pair, this summation will have just one term. But if there are more than one xy pairs that result in the same z, then we'll have multiple terms in the summation. Okay? No problem here. Yes, please. Yes, of course. So if z is a function of x, y, and q, okay, then, the probability that z takes the value z1, for example, is found by summing the probabilities of all x, y, and q triplets such that g of that triplet is equal to z1. Okay. So, any other? Okay. Now, the expected value naturally extends to functions of more than one random variable. Okay. So, expected gxy is found by summing over all x and y pairs. Now we have a double summation. Okay, we're dealing with two things, x and y, and we need to go through all values for this pair xy. That's why we need two summations. Gxy times the probability of that xy. Okay, special case when the function g is linear, like in this case this is affine, ax plus by plus c. Okay, the expected value of ax plus by plus c is, what do you think? Well, it's not hard to guess that linearity extends to this, and the expected value of ax plus by plus c is a times expected x plus b times expected y plus c. Let's just try to show this. Expected value of ax plus by plus z. Okay. In fact, I would recommend you do this on your own because it's going to be a really nice exercise for you, just to get used to doing these things. But let me do this for you once. Okay, so what are we doing? We are applying this result. Okay, so g x y, in fact we have a double summation, gxy pxy of x comma y, x goes through all possible values and y goes through all possible values. Okay, but gxy is nothing but ax plus by plus c. Okay. Okay. And remember, these were the names of the random variables. These are specific values. We already know that when you sum ax over all x and over all y, oh, I just forgot to write the PMF. So let's write the PMF. Pxy, xy. So we already know summation is linear, right? So over all x and over all y, ax, pxy, xy. Plus, do the same for y, by, pxy, xy, plus c times summation pxy. What is this summation pxy? It's the sum of the whole PMF. Dennis, what is this term, summation pxy? Sum of all probabilities. It's 1, right? So this whole term is equal to c. Now, what do we do about this term? Well, we can first of all, if you want, exchange the order of x and y, summation over x and y. We can write this as summation over y, by summation over x, pxy, xy. Right? Any problem? I just changed the order of the two summations. I can do the same here. Summation, well, here in this case, I don't need to change the order of summations. I can just take a times x out of the first summation because a and x have no dependence on y. Pxy, xy. Okay. Any problem? Let me then see what this is. What is this? That's the marginal of x because I'm summing the joint over y. Okay? So that is ax, and there's a summation at the front, px of x. This should be script x, plus, now what is this? That's the marginal of y. So summation over y, by py of y, plus c. What is this? A times x px of x. I'm going to ask particularly you. Yeah, okay, go ahead. You're like, huh? Very nice, thank you. You're like the backups of each other. Right? Answer from either of you is accepted. Okay, a times expected x. Okay, plus, what is the next one? The next one. You. Yes, please. Yes, b times ey plus c. What did we do? We just showed that expectation is linear even if we have two random variables. Okay, the linearity of expectation continues, extends to joint PMFs. Now here's an example that I think is interesting and fun. The expectation of the binomial random variable. What is the binomial random variable? Let's remind ourselves. The number of successes in n independent trials. The probability of success in each trial being p. Okay? So if you want, this is the number of heads you get when you toss the same coin n times. The value of x is the number of heads or the number of successes, and it lives from between 0 to n, which is the total number of trials. What is the probability? So let me draw a line here. X is binomial. How many parameters do I need to specify for x? 2. What are they? N and p. N and p. What is the probability that x is equal to k? Right. There are k and choose k way of choosing k locations for the successes, and for each ordering for each choice of locations, the probability of k successes is p to the k times 1 minus p to the n minus k. Of course, no PMF is complete unless its range is specified. This is valid for k between 0 and n. Okay? We know the binomial PMF. Now, if we wanted to compute this expectation, would that be pretty? Consider a summation, k times n choose k p to the k, 1 minus p to the n minus k. That's not something that I would really like to sum. But I would like to be clever and remember something. what did I tell you about the binomial? The binomial is nothing but a sum of Bernoulli random variables. Okay? So if x is binomial with parameters n and p, x, without loss of any generality, x can be written as a sum of n IID, independent, identically distributed Bernoulli random variables. Okay? Yi is Bernoulli with probability p. Okay? Good. What is the expectation of x then? Expectation of x is nothing but the expectation of the sum of these n random variables. Okay? So we have a sum of n random variables. We just showed that when you sum random variables, the expectation of the sum is sum of the expectations. So what do we have? The expectation moves inside the summation, I from 1 to n. And what is the expectation of yi? From last time, we know that the expectation of a Bernoulli with parameter p is p. Yes. So it's n times p. Okay? So this was nice because we got to apply something we just showed, which is this. And I think from this point on, there's no reason to forget the expectation of a binomial because a binomial is very simple. Binomial is the sum of n Bernoullis. Okay? N times p is the expectation of a binomial. Okay, so here's a fun example. If you didn't think this was so exciting, here's another fun example. This is the hat problem. Okay, so here's the setup. There are n people, each have a hat. Okay, that's distinct from everybody else's hats. We take all the hats, put them in a bag, and shuffle the bag. And then we let the people come one by one and select a hat from the bag without looking. Okay? So by definition, and whoever takes a hat leaves, that's not very important. The question is, what is the expected number of people who get their own hats back? What would you guess this to be? As a number, okay? The number as a probability. Do you think the expected number of people who get their own hat back, if n is 1, it's 1, obviously. If n is 2, do you think it's less than? As n increases, do you think the expected number of people who get their own hat back increases or decreases? Decreases, you think? Let's compute this. Now, here's something we have to assume. When you are any person, okay, any of these people, for any of these people, what is the probability of getting your own hat back? You have n possibilities, 1 over n. So let xi be equal to 1 if person I gets their own hat back, and 0 otherwise. So xi indicates whether person number I got their own hat or not. Okay. indicates. Remember this? I told you, right, this is the indicator function of the event that person I gets their own hat back. And indicator functions are Bernoulli random variables. The probability that xi is 1 in this example, in this problem, is, according to the model in the problem, 1 over n. So this probability decays with n. Goes like this. When there's one person, the probability is 1. And when there are two people, the probability is 1/2, and it decays like this. Okay? Probability that xi is 1. Xi is a Bernoulli random variable, so the expectation of xi is what? 1 over n. Now, what does xi have to do with the answer to the problem? The answer of the problem is the total number of people who get their own hat back. So the total number of people getting their own hats back. Now, there are n people, so let's put down n locations, 1, 2, up to n. If person 1 gets their own hats, put a 1. If person 2 didn't get their own hat, put a 0, 0, 1, etc. Okay? In other words, instead of the 0s and 1s, we could have placed x1, x2, x3, because they indicate whether or not person I got their own hat. And do you agree that the total number of people who get their own hat back is the sum of these xi's? Right? Okay. So that is the sum of xi, I from 1 to n. And what do we need? We need the expectation. Expectation of the total number of people getting their own hats, which is the expectation of the sum of xi's. We know by linearity that the expectation of a sum of random variables, whether or not they are dependent or independent, is the sum of the expectations. The expectation of xi is 1 over n for every n. So this is 1. Okay? So just like the expected number of people, if there's one person, is obviously 1. This is consistent with that observation. In fact, the expected number of people is 1, regardless of how many people there are. Okay? Again, a nice, quick, clever application of indicator random variables and linearity of expectation. I think I know what you're going to say. Let me guess. The second person is dependent. Right. Second person, if the first person got his own hat, now the probability that the second person gets their own hat is 1 over n minus 1, which is higher than 1 over n, you're going to say, right? But we're not analyzing the problem sequentially like that. In fact, the xi's are very dependent. If you know that x1 is 1, then x2 is 1 with higher probability. If both x1 and x2 are 1, then x3 is 1 with even higher probability. They are very dependent, but we don't care. Because if you just take one person, okay, from that person's perspective, Okay, there is no ordering. The probability, there is complete symmetry. Symmetry is a very important idea in counting and in probability problems. Person 1 and person I, they are by symmetry, they have the same observation. Why should they be any different? Because we have not conditioned on what happened when person 1 picked a hat. Okay, you see? It doesn't matter if they all pick at the same time or they do it one by one. It does not matter. Okay, because there's symmetry. There's no person is special. It doesn't matter whether you begin first or last. Okay, think about it. Okay. Here's another more technical example. The wording of the example is a lot of words. The idea is very simple, but the wording also carries meaning because later on we will look at Poisson distributions, and this is an example of a Poisson process essentially. But so let's see. Multi-sensor laser communication. Okay. On-off signaling can be used to transmit bits in laser communication. Okay. On-off signaling means if there's a signal, record it as a 1. If there's no signal, record it as a 0. In an on period of 1 microseconds, the number of photons detected at a sensor is a Poisson random variable with parameter lambda equals 100. Okay? So during an on period, the laser is operated. The laser shines on the detector, but of course this is a complicated physical process. The actual number of photons is not a deterministic value. It's usually modeled as a random variable, and in fact the Poisson distribution is a very good model for the number of photons that are recorded when a laser is operated for a certain fixed amount of time. In this case, it's a Poisson with parameter 100. What does this mean? We expect on average to record 100 photons, but we may actually record 200 or 0 or 50. Okay, these are all possible. In a high quality system, okay, in order to improve detection performance, 5 such sensors are used to enhance communication. Okay. What is the expected value of the total number of photons detected by 5 identical sensors? So in that example, we have x1, x2, x3, and x4 and x5. They are all Poisson with the same distribution. The expected value of x1 plus x2 plus x3 plus x4 plus x5 is just 5 times 100, which is 500. Okay. Later on, when we define Poisson processes at the end of this course, this will carry some meaning. This may be the combination of 5 independent Poisson processes, okay, with the same distribution. Okay. The total number of arrivals coming from 5 independent Poisson processes, the sum of these arrivals, if the processes are independent, is also Poisson with parameter 5 times the original. Okay? This will be the merging of Poisson processes. But right now, this is too early for that discussion. Any questions about expectation and variance? Okay. In that case, we can start conditioning next time. Please make sure to do your homework, and also you can check the lecture notes from the web page. Okay.